Okay. So if you sort of recall, up until last class, when we started talking about swap regret and correlated equilibrium, we've been in a setting where there's a single thing that we care about, sort of a single objective that we've been optimizing, and we've been calling this thing regret. Okay, but this is you can sort of relate this back to lots of other machine learning problems you might be familiar with that are not the ones we've talked about in this class. Often they're formulated in terms of a single objective. You want to, maximize accuracy or minimize error. But sometimes there's more than one thing that we care about. Sometimes we have multiple objectives. And if you like, this notion of swap regret and correlated equilibrium that we started talking about last time, you can think about that as a goal in which we've got more than one objective. We'd like to minimize regret to our best fixed action, not just overall, but also simultaneously on a whole bunch of different subsequences, in particular the subsequences on which we play each particular action. Okay, so maybe we want to minimize regret overall. We want to do as well as the best fixed action in hindsight, but also on those days for which we played action 1, we'd like to do as well as the best fixed action on that subsequence of days. And also on the days for which we played action 2, we'd like to do as well as the best fixed action on that subsequence of days. Yeah.
Is that like a multi-objective optimization? Do you mean it's like general multi-objective optimization, or is it that multiple objectives?
This is a particular instantiation of multi-objective optimization. Today, I'm going to talk about a very general multi-objective framework that this sort of swap regret thing will pop out of as a very special case. In general, the things you care about could be totally different from one another. They don't all have to be regret, for example. That's right. Yeah. So I'm not claiming that swap regret is somehow capturing like a very general multi-objective framework. I'm claiming it's going to be a particular instantiation of a general multi-objective framework, where here the objectives are all pretty similar. They're sort of minimize external regret just on these different subsequences. Okay, cool. Let's see. I appear to be very blurry on the video. I'm trying to figure out if I write the word blurry on the board, does that help it focus on something? That didn't work.
Yeah, it's super blurry. I wasn't sure if it was like the recording or just me, but yes.
Yeah, no, I can tell it's like super blurry. I blame it on the camera, not on you.
It was totally fine at the beginning, and then something happened.
Yeah. It's something to like focus on. Okay. Well, hopefully I will describe things verbally with such lucidity that it won't matter that you can't see anything. But it probably will. Okay, so what I want to do is write down a very general multi-objective optimization framework now that will be much more general than we often need. It'll be much more general than sort of this swap regret correlated equilibrium thing, but the generality will be useful for us as we explore different kinds of instantiations of it, and we'll see that getting no swap regret is going to be a very simple instantiation of this general framework. Okay, so and what do I mean by general? Well, I mean that in general, you can specify any D collection of objective functions that you care about. In fact, they don't even need to be specified up front. Like every day, there will be some increment function that sort of, in each of these D coordinates that's going to specify what you care about today. And what that increment function is can be, can vary with time and can itself be chosen adversarially. Similarly, the set of things you can do, even that doesn't have to be fixed. The action set that you have at each round and the action set the adversary has at each round, that can also vary with time and be chosen adversarially. Okay, so we're going to write down, I'm less blurry now, good. I'm going to write, oh no, shouldn't have said that. Now I'm blurry again. I'm going to write down a very general framework. Usually we're not going to use the full generality of it, but it's going to be handy when we need it. Okay. So I'm going to call this general framework the D-objective optimization game. Okay, and it's gonna be sort of an online learning kind of interaction, just like we've been studying in this class. So it's gonna proceed in rounds. I'll index by T. And in these rounds, at each round, what's gonna happen is the adversary will select an environment. Okay, what's an environment? Well, it's sort of like a little game that the adversary can choose differently at each day. Okay, so think about it as a sequence of games that the adversary is going to be choosing for the learner and the adversary to jointly play at that day. So it'll comprise of closed, convex, finite dimensional action spaces that I'll write as AT and BT, indexed by the time step. We'll think of these as collections of m-dimensional vectors. And these are going to be action sets for the learner and the adversary, respectively, as they go on to interact in this environment. And then, the environment's really like sort of a little mini game. So we've got in the environment action sets for the learner and the adversary. We're also going to define in this mini game, not just one objective function, but D-objective functions or D increments to what is going to be sort of a running optimization problem, a D-objective optimization problem for the game defined at step T. So the adversary will also choose as part of this environment a continuous loss increment. Loss increment function, which I'll call LIT, indexed by T, the time step, and also I, where I is one of these D dimensions. We're going to have D objective functions. And this is going to be for each of the objectives that we care about, there's going to be a loss increment function for that objective. And what are these things? Well, each of these functions which maps a choice of action by the learner and a choice of action by the adversary to a number between -1 and 1 is going to be convex in its first argument and concave in its second. Okay, so that's step one. I've already filled up the whole board. Let's move on to board two. Okay, so far, what's happened is that the adversary has sort of decided at each round on a game that's going to be played. Okay, the game kind of looks like it has the constraints that sort of maybe are familiar to us from our study of zero-sum games. There's 2 players. There's a convex action set for each player. There are these loss functions that are convex concave. Except now there's not just one of them, there's D of them. Let's see. If I turn the camera off for like a while, and then I count to 3, 1, 2, 3, and I turn the camera back on, it's still blurry. Okay. All right. Okay, so we've chosen this game. Oh, something happened. You fixed it. No, it worked. It worked. Thank you.
That was amazing.
Yeah. I just saw like a white thing come out in front, and then no, it's amazing. Okay. Awesome. All right, now everyone online can read this board. Okay, so first the adversary has like chosen this D objective game at each round. Next, what's going to happen is we're going to play in it. Okay, so we play in this game. So the learner goes first. The learner selects an action. AT from the action set that they have available to them at round T, and reveals it to the adversary. Okay, so it's sort of the learner is sort of playing in the minimax order. The learner goes first and reveals their move to the adversary. Then the adversary moves. And with knowledge of the learner's action, the adversary selects an action, BT, in their action set. And then the learner suffers and observes loss. LIT, evaluated at the chosen action of the learner and the adversary, evaluated at ATBT. In each loss objective I, amongst the D objectives that we care about. Okay, yeah. Okay, I should try this. Yeah. So you're saying, let me understand the. Yeah, so let me try to maybe make sure I understand your question. You're saying there's these D objective functions. They're like convex concave. I don't know how to play in a D objective game, but I do know how to play in like a one-dimensional minimax game. Maybe I'll just like sum them all up. And then I will, the summing convex concave things will preserve convexity and concavity. I'll just solve that game. Okay, so that's the construction. And you're asking like, why don't we just do that?
So I think we don't do that.
Well, let's see. So I haven't specified yet what our goal is here. So I think like if our goal was to minimize the sum of these loss functions, that would be like a very sensible thing to do. But we're going to ask for something a little bit more difficult than that. right? Like you can always reduce a multi-objective optimization problem to a one-dimensional one by just saying my new one-dimensional objective is the sum of my d-dimensional objectives. But that's a very particular thing. That's not, that's trading off, that's sort of implicitly saying I sort of value loss in each of these objectives equally, and I'm going to, trade off loss equally. It's true that that turns any multi-objective optimization problem into like a single objective one, but in a very particular way that sort of assigns equal value to each of the coordinates. So we're going to try to do something harder than that. But like in particular, like if we just use like the example of swap regret, for example, sort of a multi-objective optimization problem where the thing, what are my objectives? It's sort of like my external regret on days when I play action 1, my external regret on days when I play action 2, etc. I want all of those to go to 0. That's not necessarily implied if I minimize the sum of those losses, because external regret can be negative on some subsequences, right? So like it's possible that I minimize the sum of my external regret on these different subsequences, but I do it by making my regret negative on some of the subsequences and positive on others, which is different than making it 0 everywhere. Good question, though. I mean, ultimately, like, you're not totally off base. Like, we're gonna do something like this. Like the algorithmic approach in the end is that each round we're going to solve a zero-sum game, like a one-dimensional zero-sum game, where the objective is some like weighted sum of these losses. It's just that like we're not going to use the uniform weighting. We're going to try to be clever and adaptive about what the weighting is. Yeah, but it's like a very good observation that like taking sums or even weighted sums of these loss functions preserves convexity and concavity and will sort of take us to like a one-dimensional min-max problem, which is, something we know how to deal with. Okay, good question. Other questions? So this is the environment. I haven't yet like said what our goal is, but is the sequence, is the sort of interaction with the adversary clear? Every day, basically, the adversary chooses a d-dimensional zero-sum game, like a zero-sum game with d-objective functions. We don't know how to deal with that yet. But then we like play in that zero-sum game against the adversary in the min-max order. The learner picks an action, the adversary best responds with some action, whatever that means. Again, D objectives, not clear what that means. And then like we realize this loss, it's not just a one-dimensional loss, it's like a d-dimensional loss. And that's happening every round. And so it's going to somehow, aggregate, and we need to specify what our objective is. Yeah. Well, I mean, you're saying at step two, when the learner is choosing the action, certainly they don't see the adversary's action. That doesn't happen until step 3. So it's the min-max order. They do know the environment. So they know their action set. They know the adversary's action set. They know what the loss functions are. Good. Okay. Okay, and these things add up. So, like at time t, at the end, the cumulative loss in dimension D, or dimension I, let's say, amongst the D possible dimensions, is just the sum of the per round loss in that dimension over the time steps. Okay. So right, as we've talked about already, like if the learner's goal was somehow to minimize the sum of these losses, then we could have just turned this into sort of like a single dimensional zero-sum game at each round by summing up the losses. The difficulty is that our goal is not going to be to maximize, it's not going to be to minimize the sum of the losses, but to somehow minimize the maximum of the losses. We're going to want our loss in every single objective and all d of these coordinates to be as small as possible somehow, where we're going to need to define like a benchmark, like what does as small as possible mean, but that's the goal. Okay, we care about minimizing the maximum of the losses. Okay, so like hearkening back to swap regress and correlated equilibria, what we care about is that the maximum regret on any of the subsequences defined by the actual actions we play should tend to 0, not just the sum of the regrets. Okay, and the reason why the sum of the regrets doesn't imply a bound on the maximum of the regrets, and more generally why the sum of the losses doesn't imply a bound on the maximum of the losses, is because the losses are not non-negative. They could be positive or negative, which is something that's true, for example, of regret. Okay. Okay, good. So in this environment, we need to think about what is a reasonable benchmark, right? Like, again, like as we've been studying in this class, this is not a distributional setting. It's not like there's some underlying distribution of environments and actions that we can sort of speak of optimality with respect to. It's an adversarial setting. And so we need to think about the kinds of benchmarks we can talk about, things like regret that make sense in adversarial settings. And here, since there's sort of d different objective functions, we need to think about like what is a reasonable benchmark with respect to which we can measure like some kind of multi-objective regret. Okay. So, the way I've set things up, right? The learner is like playing in something that looks like a zero-sum game, except it's a d-dimensional zero-sum game in the min-max order, right? First the learner moves, then the adversary gets to best respond. So, going first is always a disadvantage. Maybe taking inspiration from the min-max theorem, an aspirational benchmark, at least, would be to try to do as well as we could do as if the role of the learner and the adversary were reversed, right? Like maybe a reasonable benchmark is, in hindsight, given the sequence of environments that we knew we were playing with, to do as well somehow as we could have done had the roles of the learner and the adversary been reversed. Okay. So that's what we're going to try to do. Let's fix an environment. At round t, which remember is defined by an action set for the learner, an action set for the adversary, and a collection of loss functions for each coordinate I ranging from 1 to d. Then we'll say that the adversary moves first. Value at round t is, we'll write this as VAT, A for adversary, the maximum over all of the actions that the adversary could choose. Okay, adversary goes first, of the minimum over all of the actions that the learner could choose. Learner goes second. But what does the learner care about? The learner cares about the maximum over all of the coordinates of the loss in that coordinate when the learner plays A and the adversary plays B. Yeah. Okay, good. Well, we can hear you, Natalie, if you want to just speak up.
Oh, okay. I tried before and I wasn't sure if you could hear me, so I didn't want to like, but you can hear me?
Now I can hear you, yeah.
Okay. So my question was about the model and whether this is a generalization of the learning with expert setting. And if so, like what the game would be, because it doesn't seem like you can have arbitrary losses here.
What do you mean arbitrary losses?
So I guess maybe I'll stick with the first question of like, is there a way to see this as a generalization of the learning with expert setting? And does it have something to do with like fixing the game in a particular way every time?
Yeah, it's definitely a generalization of the learning with experts setting, although ultimately, we're going to solve it using the tools we derived for that setting. But basically, any kind of fancy regret bound you're aware of, like adaptive regret, where we care about regret not just overall, but on contiguous subsequences of time, or, group-wise regret, or calibration, or Blackwell approachability. Those are all going to be like special cases of this. So I think of learning with experts as sort of an online learning setting where there's like one thing you have singular focus on, which is just your marginal regret over time. And this is going to be something that lets us focus on more than one thing at a time.
Okay, so I guess the thing I'm confused about is, so when we think about the person, the learner, right, and what they're trying to do, it feels like there's one way in which a learning with expert setting is like a little harder than this, in that at the time that the learner has to choose their action here, they at least know a finite, that they know where the game is, right? They know like all the possible losses they could experience. Well, in the learning with expert setting, when they choose their action, those losses could be totally arbitrary.
Oh, sorry. So you're saying here they know the losses, but in the learning with expert setting, they don't know the losses?
Right, like you don't know any sort of structure on what the losses could be.
Oh, sorry, no. So the learning with expert setting is a very special case of this, where there's, like the loss function, but you don't know the actions for the adversary, right? So like, for example, the actions for the adversary could be, if say you've got K experts, like K-dimensional vectors that tell you what is the loss if you play each of the experts, right? So it's like, I've put more structure here, but this is only making the setting more general. It can incorporate the setting where, you experience the loss of the expert you play, and you don't know what that is because although you know the loss function, all the loss function tells you that if you play expert 5, you're going to get loss, C5, where C is the action of the adversary.
I see. So you don't know, but like if you knew their action and your payoff and your action, like in this setting, you know what your loss is, or even then you wouldn't know?
You would know your loss if you knew your action and their action. But in like the learning with expert setting, their action would be to choose a vector of losses that tells you what's your loss for each of the actions you play.
Okay.
Right. So that would be like,
that
would be a special case of this where the loss function was exactly the same every day and just said, it's like the inner product of your distribution and the adversary's cost vector.
Okay, that makes sense. Thanks.
Okay, cool. Oh, yeah, and just sort of, right. In the examples I mentioned so far, like it didn't use the fact that like the action sets could change with time. But for example, this lets you derive algorithms for like the sleeping expert setting, where there are actions that you're not allowed to choose at different time steps. That's sort of where, that's one of the places where it's useful to have like the action set change over time. Okay. So yes, what is this adversary moves first value of the game? Well, it sort of looks at like a single stage game. So it says, okay, suppose the thing you care, suppose we're just going to play in this environment, once, like I'm zooming in on like a particular stage, like stage 5. I'm saying, okay, we're just going to play in this environment once, but the adversary gets to go first, and then you get to best respond. And the thing you care about is minimizing the maximum coordinate of any of these D loss functions. Okay, the adversary moves first value tells you, given that you care about the maximum of the loss functions, given that we're going to play this once, the adversary is going to tell you what they're going to do, and you get to best respond. What is the lowest maximum value that you could guarantee? Okay. Okay. Now, you guys are now all experts in the minimax theorem, and so it's probably tempting to sort of go through the following chain of thought. You say, well, these loss functions in each of the D coordinates, they all seem pretty well behaved. You know, they're convex, concave, and bounded. They satisfy the conditions of the min-max theorem. We're playing in an interaction where the learner moves first and then the adversary moves. And we're sort of saying now that we'd like to compare ourselves to an interaction which the adversary moves first, and then we get to best respond. Like maybe we can just apply the minimax theorem to this objective and be done. And unfortunately, we can't because of the max. So, by the way, like if what we cared about was not the max, but the sum of the losses, we could do that at this point, where the sum of these convex concave losses will also be convex concave. But the max, unfortunately, is not going to preserve concavity. And it's not just a technical obstruction. Like if this is what your objective function is, the min-max theorem is just false. It just doesn't hold. Okay, so let's like see an example of that. Yeah. Oh no, Eshwar is going to give us an example. Oh boy, I'm not smart enough for that. Let me give you a much less general but more concrete example. Okay. Wait, so here's like a simple counterexample to the minimax theorem, if you were tempted to apply it here. Okay. So what are the action spaces? Well, the action spaces for both players are just the simplex over D dimensions. Okay, so what you're going to choose, if you're the learner or the adversary, is just a distribution over D things. So you're going to choose like D numbers that are non-negative and sum to 1. Okay, and what's the loss function? Well, for each coordinate in, the actions are going to be these D-dimensional vectors. We're going to have a loss function for each coordinate of the vector, basically. For each coordinate of the loss function, the loss in coordinate I, if I play distribution A and the adversary plays distribution B, it's just going to be BI minus AI, just the difference between the weight that the adversary put on coordinate I and the weight that I put on coordinate I. Okay, so can anyone tell me what is the adversary moves first value of this game? If what I care about is the maximum loss over each of these D coordinates, okay, so I care about sort of the maximum difference between the adversary's weight on element I and my weight, and the adversary gets to move first and pick a distribution. I get to look at that distribution and then best respond. What value of the game can I, what adversary moves first value of the game can I guarantee for myself? Eshwar. Exactly. So the adversary moves first value of this game is 0, right? I have like a very simple constructive strategy to obtain this. I just copy the adversary's move, right? Like if the adversary plays distribution B, I think to myself, what should I play? Well, I'm going to play the same distribution. My action space is the same as theirs. I'm going to play A equals B. This is going to guarantee that this difference is 0 in every single coordinate. Okay, and I can't do better than that. I can't guarantee a negative value because all of the numbers have to sum to 1. Okay, so the adversary moves first value of this game is 0. It's great. So this is like a winning game for me if I get to go second. Okay, but what if I have to go first? Like if I have to go first and tell the adversary what distribution I'm going to play, then how well can I do? Yeah, maybe D. Right. So if learner goes first, you know, what we might call like the learner moves first value of the game is at least 1 minus 1 over D is 1 minus 1 over D. How come? Well, you know, I'm going to play some distribution over these D things. But, you know, a distribution has to have weight summing to 1, which means that I can't put weight 1 everywhere. There's going to be at least one coordinate that I'm forced to put weight less than 1 over D on, or less than or equal to 1 over D, right? That, you know, like if I want to maximize the weight on the minimum coordinate, I have to play the uniform distribution, which puts weight 1 over D everywhere. Okay, so there's going to be some index I such that AI is less than 1 over D. What's the adversary going to do? Well, the adversary can just put all of their weight. They can play a point mass distribution on the coordinate that I put minimum weight on. Right? So they can put weight 1 on some coordinate for which I put weight 1 over D. That coordinate, and therefore the maximum over all of the coordinates, will have loss value that's at least 1 minus 1 over D. Right? Like, so these losses are bounded between, you know, they're upper bounded by 1. So this is sort of like the worst possible example falsifying the minimax theorem in this setting. Like if the adversary moves first and I have the advantage of going second, if I'm the learner, I can guarantee value 0. But if I have to go first, as I actually have to in this environment, and the adversary gets to best respond, the adversary can guarantee value at least 1 minus 1 over D, which, you know, as D gets bigger is approaching 1, which is the maximum possible value. So this is sort of like the worst case possible if I was like hoping the minimax theorem was true in this setting. Does that make sense?
Can you hear me?
Yes.
So just a quick question about this, like thinking about how, like, so say that D was 2, right? And so now there's only, it's like a matrix with two, it's like a distribution over 2 things, right?
Mm-hmm.
Which now should sort of look like a one-dimensional thing because it needs to add to 1. And so, like, I guess I would have expected in that sort of setting you would sort of get back the minimax result from just the non-vector valued game, but that seems like you would still get 1/2.
Exactly, yeah. So even in 2 dimensions, the minimax theorem doesn't hold here. You need it to be 1-dimensional. So it's true that the fact that I have to play a distribution means my strategy space, if D is 2, is effectively 1-dimensional, but the dimension of the objective function is still 2-dimensional, right? And this is sort of getting at sort of a fundamental fact that the minimax theorem is like very fundamentally about 1-dimensional functions. Even in 2 dimensions, it's just not true.
Right.
Even if we assume, you know, nice convexity and concavity.
If you were only allowed to have these loss functions be like in expectation over this distribution, you'd be fine. But because you're actually allowed to look at what the distribution that was actually played, you're not fine.
There's many ways in which you could be not fine. Like the minimax theorem in general does not hold in more than 1 dimension.
Yeah, but like if you took, I guess I'm just trying to say, like, this feels very similar in spirit to like you have D moves and you're playing a distribution of those D moves, right? But like the difference is here we're allowed the loss function to be about like the difference, Like this is not in that sort of setting, like this loss function wouldn't make sense.
So like I don't want to over-index on this particular
Okay,
example.
sure.
Like I picked a particularly simple example to show that the minimax theorem doesn't hold in this setting, but
Yeah.
like many examples would work because the minimax theorem doesn't hold in greater than one dimension. So like it's not because these are it's not somehow
I
like
just want to
particular
draw
to
a
the fact
sharp
that these are
distinction.
distributions.
I guess I want to draw a sharp distinction because it does seem really similar and like here, but we're not talking here about playing a distribution over pure actions. We're talking about playing, like you're actually playing the vector.
Yeah, like we don't even have to use the word distribution. Like your action
Right.
space is just some set of vectors, and this is
Yeah.
what the losses are.
Cool.
Right, and otherwise everything, except for the max, except for the fact that there's d dimensions and I have a max here, everything here otherwise satisfies the conditions of the minimax theorem, right? Like your action sets are convex, the loss functions are actually linear in this case, right? Like what's going wrong is that there's d coordinates that we're taking the maximum of. Yeah, sure.
Oh, this is one thing that and it's that is just one number being displayed here. And the two games that we're going to depend on the functions and the exact negative
Yeah, that's right. Yeah, exactly, good. Yeah, in the two-dimensional case, you're just like picking a number. We want like the numbers to match. Yeah, right, like in the two-dimensional case, you're picking a number, and the loss is essentially the maximum of these two coordinates is really just the absolute value difference between these two numbers.
Yeah.
Right, and so like the absolute value difference, right? These were linear functions, but the maximum of the two coordinates is this absolute value difference, which is convex but not concave. Good. Okay. Does this make sense? So remember, where were we? We were, like we set up this whole multi-objective optimization game, and we were saying, like the thing we care about is kind of this, like we care about the maximum loss in all of the coordinates, except not at a single round. We care about bounding the maximum loss cumulatively. And we were like hunting for a benchmark. We were sort of saying, okay, well, if the world worked in multiple dimensions the way it works in one dimension, maybe there's like a minimax theorem here. We could aim to do as well as if the adversary was forced to move first, and we could best respond, even though we actually have to play in the reverse order. And then we saw this counterexample that sort of showed us that the minimax theorem doesn't hold in this setting. And so, at this point, like, what's our move? Like, do we give up on this and try to define a weaker benchmark? And maybe I want to sort of reflect on the analogous thing in sort of the one-dimensional no-regret problem. Remember, we did use the minimax theorem to derive the exponential weights algorithm, to derive a no-regret algorithm. And how did we do that? We sort of said, okay, in some sense, we said, let's look at a stage game, right? If in a stage game, at a single round, the adversary was forced to tell us their cost vector up front, and then we got to turn around and choose our action, then on that stage game, we could have like zero regret. We would choose the action that had the lowest loss, right? So we sort of said for this one-dimensional problem, like the adversary moves first value is 0, and so that's what we're going to compete with. We can do that at every round, and so our regret will be essentially 0, summing up over all of the rounds. Okay, so there, like we did just directly compete with like the adversary moves first value. Here, things are a little different. What this means is that round by round, it is not possible to compete with the adversary moves first value. Like round by round, like if the game looks like this, for example, the adversary moves first value can be extremely far away from the learner moves first value. But that does not necessarily mean that we cannot compete with the adversary moves first value in aggregate over all of the rounds, because we don't have to, like our our objective is not to compete with the optimal thing round by round, to minimize the maximum loss round by round. Our objective is to minimize the maximum loss cumulatively over rounds. And although we haven't, like in sort of the derivation of like a one-dimensional no regret algorithm, we didn't really exploit that. We sort of, in this minimax argument deriving exponential weights, competed with the, maxi-min value round by round. That was how we did it cumulatively. That's not necessarily the only way to do it. We have additional flexibility in the fact that we only need to compete on average over a large sequence of rounds. That means we're not necessarily dead in the water just because we can't compete with the adversary moves first value one round at a time. This is a fundamental difference between one-dimensional problems, one-dimensional minimax problems, and multi-dimensional minimax problems. Okay, so even though this example shows us that it is not possible to compete with the adversary moves first value at a round-by-round basis, it does not mean that it is not possible to approach that value over time. So let me define something that I'll call adversary moves first regret. Or AMF regret for short. Let's fix the transcript. Pi t in this sort of d-objective multi-objective optimization game. And what does a transcript consist of? Well, for each of the time steps t, there was an environment, so a strategy space for the learner and the adversary. There was a collection of loss functions. In each of the d coordinates. And then there was the record of what actually happened, the actions played by the learner and the adversary in all t rounds. The adversary moves first regret, the AMF regret, is the maximum over all of the coordinates of the cumulative loss that the learner experienced in that coordinate. So this is the thing they would like to be small. The maximum cumulative loss over all of the D objectives, the maximum of the D objectives you care about. Well, small compared to what? Well, the thing we're going to compare it to in this regret statement is the sum of the adversary moves first values of the game. Okay, or just written another way, it's the maximum over all of the coordinates of the sum over all of the rounds of the loss experienced in coordinate I at round t minus the round t adversary moves first value of the game. Okay, so maybe just like to sort of build a little bit of intuition for what kind of object this is, our framework and the statement of this regret bound allows us the flexibility that the environment and therefore the adversary moves first value of the game is different at every round. But suppose it's not. Suppose you're just playing the same game at every round, which will be like a common case. Then, there's just a fixed adversary moves first value. Okay, you're playing the same game over and over again. It's not possible to round by round achieve the adversary moves first value of the game. But what this is asking is that averaged over rounds, if I look at the maximum loss in any of the t coordinates, the maximum accumulated loss over t rounds of any of the d coordinates, that be at most t times the adversary moves first value of the game. So it's not saying that round by round you can, it's not saying anything, it's just a definition. But were I to tell you that you could get constructively against an adversary moves first regret tending to 0, that would say, although you cannot match the adversary moves first value of the game round by round, if I let you play repeatedly against an optimal adversary, on average over the rounds, you can approach that value. Okay, so this is closely related to something called Blackwell approachability. This is some generalization of Blackwell approachability to a setting in which the thing you want to approach, which is sort of encoded in this setting as the environment, is allowed to change from round to round. Okay. Questions about this quantity, this benchmark?
I have a question. Can you hear me?
Yeah.
Yeah. So in this example, like say that you were playing this exact hard instance that you showed here for the single round case, and say that this was the same game every round in this repeated game.
Mm-hmm.
So can you help give some intuition for why there's something more interesting you can why don't you still get that 1 over d gap?
Yeah, good. So yeah, it's good to think about, because this is again like a phenomena that doesn't occur in the one-dimensional case, like the Minimax theorem and its equivalents with no regret algorithms that we saw sort of tells you in the one-dimensional case the kinds of regret bounds you can get, the kinds of things you can approach over time, they're sort of the same as what you can get in a single round with the Minimax theorem. And what we're going to be seeing here is that in higher dimensions, and sort of Blackwell approachability is the sort of multi-dimensional generalization of the Minimax theorem, there's going to be this gap where, in a single stage game, I can't compete with the adversary moving first, but I can do it repeatedly. And how, what if we're playing this one? Well, the fact that I'm playing repeatedly lets me sort of adaptively focus on the coordinates I'm doing badly on, right? So what's going to happen, at round 1, I pick some vector. The adversary singles out the smallest coordinate of that vector and puts all of their weight there. And now what's happening? Well, there's this one coordinate, coordinate 5, where my loss is now really high, but my loss is actually pretty good in the other coordinates. It's even a little bit negative. And so what I want to do at the next round is play so as to force the adversary into a trade-off. If they somehow I want to force the adversary so that if they want to try to, I want to force the adversary to not be able to make the same coordinate have really high loss anymore. They won't be able to make the same coordinate have high loss. Maybe they'll make some other coordinate have high loss, but if the hope is that if I coordinate my actions across rounds correctly, that the adversary will sort of be forced to dilute their penalties across these coordinates and maybe, force cancellations. Note here that if the adversary focuses on coordinate 5, I have loss close to 1 in coordinate 5, but I actually have negative loss in the other coordinates. Maybe I can force the adversary to play so that in every coordinate, as averaged over time, the loss is close to 0, even though at every round there's some coordinate in which the loss is high. That's sort of going to be the idea. Does that make sense?
I see. So it's not that the way you're computing the loss here is that you take the loss in every round and add it up, like this single round loss. It's you're going to look at the distribution, the sort of average vector you played over time and the average vector they played over time, and compute the loss on that.
Yes, so I am adding up the losses, right? The cumulative loss in coordinate I is just the sum of the losses in coordinate I. But the difference is that I'm taking the max The thing I care about is the max of the aggregate losses, not the aggregate of the max losses. Right? So like, if what I cared about was the sum of the max losses, then there would be no difference between the stage game and the repeated game. We'd just be summing up my sort of, like the duality gap basically between the stage games, and there'd be no difference. The reason there's a difference here is because the thing that I care about is the maximum aggregated loss, and that is different than the aggregated max loss. But this is sort of, this example sort of says I cannot compete with the aggregated max loss or even the stage game max loss. That does not preclude me from competing with the max aggregated loss.
Okay, sure. Thanks.
Let's see, which is the right and which is the left? Yeah. Which is the right? Is the right all the way over here? This one, here's the right. Okay. So this is, this is the value at round t. So it can be different, because the environment can be different at every round. This is indexed by t. It can be different. So this is not a fixed number in the round. Exactly. This is sort of the sense in which what I'm talking about now is somewhat more general than Blackwell approachability. It's that the environment can be different at every round. What we're competing with is the sum of the adversary moves first values across the t rounds. That those can be different numbers at every round. If I was thinking that what is part of the overall dimension of the distribution, and just lay that over and over. Right? But then this problem is that that's right. That's right. Yeah. So it's taking advantage of the fact that sort of the worst case loss, you can force the worst case loss to be in a different coordinate at each round. And so it sort of washes out in the average. Right. So maybe like to summarize, this example shows that the adversary can force that the loss in the maximum coordinate is high at every round, but cannot necessarily force that which is the maximum coordinate is the same, and therefore cannot necessarily force that the maximum of the aggregated coordinate-wise losses is high. And that's the thing that we're hoping to take advantage of here. Good. Yes. That's right. Yeah. So like everything we've talked about would be true even if we were just playing in a fixed environment at every round. But here the adversary even has control over the games that we're playing. The adversary is the one who chooses the environment and the loss function at every round. That's right. I mean, the learner is going to have enough cleverness to try to, like, despite this control that the adversary has, force that the loss not be too high in aggregate in any coordinate. So it's not clear how to do that yet. We're going to have to design algorithms for the learner, but like that's the kind of thing we're going to have to hope for if our goal is going to be to give algorithms that are going to guarantee that the adversary moves first regret of the learner is small. Good. Okay. Okay. Let me show you the algorithm that we're going to analyze. And let's see, should I show you the algorithm first and then tell you about it, or tell you about it first and then show you? Let me show it to you first. Let me write it on the board. And it's going to maybe look a little mysterious written on the board. Then I'll explain to you what's going on. Okay. You can think of this algorithm as really being a reduction from this multi-objective problem we've defined, in which we care about adversary moves first regret, to a just single objective online linear optimization problem, the kind of thing we've been studying throughout the whole class. Things that are solved, the problem that is solved by things like the exponential weights algorithm. Which is to say, in the algorithm I'm about to write on the board, it's going to take sort of as input a subroutine, which is an online linear optimization algorithm, and make use of it. So if we have one of those things that has like a regret bound, and we do, because that's what we've been studying in this class so far, we're going to have like a concrete subroutine that we can plug into this algorithm and get adversary moves first regret guarantees out the other end. Okay, so this is a reduction from AMF regret to external regret, simple regret. Okay. And what do I mean by a reduction? Well, what I mean is that I'm assuming that we're given an algorithm that I'll call ALG, which is a sequential linear optimization, linear maximization algorithm. Operating over the simplex, over the d-dimensional simplex, and accepting cost vectors CT, which are going to be d-dimensional vectors with entries bounded between -1 and 1. Okay, so we're going to make use of the subroutine, which we can instantiate in various ways. What is the subroutine? It's something like multiplicative weights or exponential weights. Every day it's choosing a distribution over d objects. It's expecting every day a vector of costs. And what it's going to try to do is play over these d coordinates so that its cumulative cost is as high or nearly as high as the highest cost coordinate in hindsight. Okay, so we're going to talk about linear maximization rather than linear minimization, which is the thing we've been primarily talking about so far, but it's the same thing if you just multiply all the costs by -1. Okay, so this is what we're given. We're going to get bounds in the end that sort of will be in terms of the regret bound of this algorithm we're given. And now we're going to make use of it. So for T rounds, for capital T rounds, little t ranging from 1 to capital T, what are we going to do? Well, we've got this subroutine here. What's it doing? It's maintaining a distribution over its d actions. Let's get that distribution. Okay, so we'll obtain the distribution over the d actions being maintained by our online linear optimization algorithm, like the multiplicative weights distribution, say. Now we'll define a zero-sum game, like a standard one-dimensional zero-sum game of the sort we've been talking about. In which min's actions our AT, the action set that the adversary gave us in today's environment. Max's actions are BT, the action set that the adversary gave himself in today's environment. And the utility function is as follows. Min plays A, max plays B, then the utility is the sum over the D coordinates of the loss of PIT times the ith coordinate of the loss evaluated at the actions chosen by min and max, A and B. And then what are we going to do? We'll compute a minimax equilibrium minimax strategy for this game. And in the outer multi-objective optimization game, that's what we'll play. We'll play AT. And we'll observe the adversary's action BT and report costs CT to our online linear optimization algorithm, defined so that the cost in the ith coordinate is just the loss obtained in the ith loss function given the actions actually played. Okay, so let's look at what the algorithm is doing and then maybe talk through why it's doing it. Okay, so we've got some concrete, online linear optimization algorithm, something like multiplicative weights or gradient descent, or call it the perturbed leader or exponential weights. We've seen a bunch of these things. Each of them, what it's doing is maintaining some distribution over these D coordinates. That's what it does. Now, here comes round T. The adversary tells us some environment, okay, an action set for us, an action set for themselves, a loss function in each of D coordinates. And what we're going to do is we're going to boil that down into a one-dimensional zero-sum game. What's the zero-sum game? Well, we'll take our action set, we'll give the adversary their action set. The only thing interesting we need to do is take this D-dimensional objective of the environment and boil it down to a one-dimensional objective. How are we going to do that? Well, we're going to take a weighted sum of the losses. Okay, but this isn't going to be an arbitrary weighted sum. It's not going to be like the uniform sum over all of the losses. It's going to be weighted by the distribution of the online linear optimization algorithm at this step. It'll be weighted, for example, by the multiplicative weights distribution. Okay, so what this weighting is going to be different from round to round because the online linear optimization algorithm is updating its state from round to round. Okay, so the objective function today is just the weighted sum of the D coordinates where the weighting corresponds to the weights that multiplicative weights puts on each of these D experts. Okay, then we're going to solve that game. We're going to find a min-max solution to that game. And that's what we're going to play. That's the strategy we're going to play. Then the adversary is going to do something after, right? The adversary best responds to us. We eventually see what that is. And we need to, we're really relying on this online linear optimization algorithm, multiplicative weights, to provide us with a distribution at each round. And so we need to give it the feedback it needs. It needs to learn what is the cost in each coordinate so it can figure out how to update for next round. Well, what are the costs we're going to give it? The cost we give it for its ith action is just the loss we experienced in our ith objective function given what was actually played. Yeah. From round to round. Although everything here is in one round, so it's, fixed for, like, that's right. Yeah. So tomorrow the action space might be totally different, and I'll have to solve a different, a minimax equilibrium of a different game tomorrow. It's not going to be a problem. Yeah. Which is good. But right, like if you want, right, like a special case of this is where the environment is the same every round. The action space is the same every round for the learner. And the adversary, the form of these loss functions is the same. Still, you'd be solving a different zero-sum game at every round because the utility function would be changing as the weights, from multiplicative weights changed and differently weighted the different objectives. And yeah, like indeed, like actually more stuff can change in our setting, like even the action spaces can change, the form of the loss functions can change. That's okay, we can still run this algorithm. Yeah, so is it clear what the algorithm is doing? Maybe it's not clear yet why it's doing it, but yeah, is what the algorithm is doing clear? Okay, and you can already see, it is somehow a reduction from this multi-objective optimization problem to a single dimensional optimization problem, like a single one-dimensional minimax problem that's happening in this step, where we define the utility function to be a one-dimensional utility function, taking a particular weighted combination of the laws. Yeah.
Already there's some that would expect some motivation to multiplicative weight, for instance, to sort of put more weight on the but not completely sort of thing. Not something clever to kind of it goes along with if you're going to use the concept of your coordinate I, the algorithm to the I not something.
That's right. Yeah. So like repeating this a little bit for those of you online, Natalie. Eshwar sort of pointed out that already in the algorithm, maybe we're seeing some of the intuition in our example for why, for what you might try to do over a sequence of rounds. If you had really high loss in coordinate 5 at round 1, then multiplicative weights, which is trying to maximize loss here, like we're running it as online linear maximization, it's going to upweight coordinate 5. And so coordinate 5 is going to matter more in the problem we solve tomorrow. And so in some sense, the coordinates that historically we have done worse on, we've got some feedback loop that makes those coordinates relatively more important in tomorrow's optimization. So maybe that's some positive intuition, at least, that we're not doing something crazy. Like there's some feedback loop here that is dynamically upweighting the objectives that historically we have done relatively worse on, that maybe makes them matter more for tomorrow's optimization. So you can sort of, maybe some intuition for this is where we decide to focus our attention. We have D loss functions. If we divide our attention amongst these things, we could divide it uniformly. Right, we can't put all of our attention everywhere. It's like our attention, maybe think of that as a distribution. But we're going to sort of focus our attention differentially across different objectives. And since we're doing that with like a no regret learning algorithm, like maybe some intuition is that what it's going to be doing is focusing our attention more on those on those coordinates that historically we have done relatively more poorly on. Good intuition. Okay. So clear what the algorithm is doing? Okay, so why is it doing it? So maybe if you want, so we've got this copy of, multiplicative weights, say, floating around. That is, multiplicative weights is not choosing what actions we take directly. Multiplicative weights is just used to define the game that we solve to choose our actions. So maybe it's helpful to think about what multiplicative weights is doing here as being like an outside observer that is kind of rooting against us. Okay, like multiplicative weights is kind of cheering for the adversary here, because what we want to do is minimize these losses, but we're running multiplicative weights as an online linear maximization algorithm where the thing it's trying to maximize are the losses, right? Like it's every day choosing a distribution over losses in the hopes that it's put its weight on high losses. Multiplicative weights here is going to be happy insofar as the losses are high. Okay, so think about multiplicative weights as, a fan of the adversary who's in the stands cheering against us. Okay, and they're actually like, they're not just cheering against us, they're like betting against us. They're putting weight on these different losses, and they're actually pretty good at betting in that they have a regret guarantee. Okay, right, like multiplicative weights has this regret guarantee. So they know, like, what is the loss of multiplicative weights? Right, if you think about it, right, multiplicative weights is choosing a distribution every day on the coordinates of our loss, and the gain of multiplicative weights, the thing it's trying to maximize, is the expected loss we experience over those coordinates in expectation over its own distribution. Okay. Now, multiplicative weights is pretty good at distributing its weight. It has this regret bound. And so the guarantee of multiplicative weights is that on average over time, its cumulative gain is going to be up to low order regret terms, at least as good as the gain of the best coordinate in hindsight. Okay, well, what's the best coordinate in hindsight? The gain that it gets in each coordinate, in coordinate I, is the per round loss that we get in the ith objective. So from multiplicative weights perspective, the best coordinate in hindsight corresponds to the objective amongst our D objectives that has highest cumulative loss. Okay, the max overall of our objectives, of the cumulative loss of that objective. That is exactly the thing that we are trying to make small. Okay, so from multiplicative weights perspective, the sort of gain of the best expert in hindsight is exactly the cumulative loss of the largest, of the coordinate of the objective that has largest loss for us. So the benchmark for multiplicative weights is exactly the quantity that we would like to make small. And the regret bound for multiplicative weights says that the cumulative loss of multiplicative weights is only going to be larger than this thing that we would like to make small, right? The cumulative gain of multiplicative weights in this case, up to regret terms, is only going to be larger than the maximum loss in any coordinate. The maximum cumulative loss in any coordinate. Exactly the thing that we would like to make small. Yeah. That's right. There's no I here. That's right. Well, so first of all, that's how it's written here, right? The max is over the Li and not over the values. Right, but what's going on, right? So we've set things up so that the benchmark with which multiplicative weights is competing is exactly the quantity that we would like to guarantee is small, the cumulative loss of the maximum coordinate in hindsight. And multiplicative weight successfully competes with that benchmark. It's going to have cumulative gain that is as high as our benchmark up to low order terms. And so if we can arrange things so that multiplicative weights has small cumulative gain, because the cumulative gain of multiplicative weights is only going to be bigger than our benchmark value, that will mean that our benchmark value is also small. Right? Multiplicative weights, because it's rooting against us and is playing well, it has a regret bound, upper bounds our benchmark value. Multiplicative weights does better than our benchmark, has higher loss than our benchmark. So if we can arrange things so that multiplicative weights has small cumulative loss, the only way that can be true and still be consistent with its regret bound is if the cumulative loss of the maximum coordinate over these d objectives we care about is also small. That's the only way the following two things can both be true, that multiplicative weights has small cumulative gain and the cumulative gain of multiplicative weights is at least as high as the cumulative gain of the best fixed coordinate in hindsight. The only way those things can both be true is if the largest loss coordinate in hindsight has small loss, which is what we would like to arrange. Okay? And so having set this up in this way, having arranged things so that multiplicative weights is cheering against us effectively, we can rephrase our problem as at every round trying to play so that multiplicative weights, or whatever online linear optimization algorithm we're using, has small gain that day. If we can promise that no matter what happens, no matter what the adversary does, we have no control over what the adversary does, but if we can arrange things so that for every action of the adversary, multiplicative weights has small gain on day 1, and has small gain on day 2, and has small gain on day 3, then its cumulative gain will be small, and therefore the maximum loss in any of our coordinates will be small. Well, what is the loss? What is the expected loss of multiplicative weights, or whatever online linear optimization algorithm we're using? What is its expected loss at day t? Well, it's this. This is the expected loss of multiplicative weights at day t. It is just the sum over all of the coordinates of the loss that will be realized in that coordinate, which is just the gain that we're going to feed to multiplicative weights in that coordinate, times the probability that multiplicative weights plays that coordinate, times the weight it puts on that coordinate. So what is this utility function? This utility function is nothing more than the expected gain of multiplicative weights at day t. And so what is this algorithm setting out to do? Well, it's defining a zero-sum game where what the learner is trying to do is explicitly to minimize, in a min-max sense, to minimize in the worst case over what the adversary might do, the gain of this evil copy of multiplicative weights, which is rooting against our valiant learner at that day, right? The learner is trying to play so that the gain of multiplicative weights that day is small. No matter what the adversary does, they're trying to optimize that in a min-max sense. Okay? And so to the extent that it can do that, because multiplicative weights has a regret bound, it will arrange things so that the maximum loss, maximum cumulative loss over all of the coordinates is small, because the cumulative gain of multiplicative weights will upper bound the cumulative loss of the learner. Okay, and it's going to turn out that how well is it going to be able to do, right? Like, it's going to be able to obtain the value of this game. It's going to turn out that the value of this game at each round t is upper bounded by the adversary moves first value of the multi-objective optimization game. Okay, so we're not able to compete with this in the multi-objective game round by round. We saw an example of that. But we're able to define this one-dimensional game that has the same value, and we can compete with that round by round. And because of the regret guarantees of multiplicative weights, that's going to mean that cumulatively in the multi-objective game, we can compete with the adversary moves first value, round by round. Not round by round, cumulative. Okay, so let me just write down what the theorem is going to be, and we'll prove it next class. Okay, so this algorithm's a reduction, right? Like we plugged into it an online linear optimization algorithm, like multiplicative weights or something else. So the guarantees of this algorithm are going to depend in some way on what the regret guarantees of the subroutine we plugged into it were. Okay, so let's suppose that ALG, the online linear maximization algorithm we plug in here as a subroutine, has a worst case regret bound of R of t. Meaning, if we look at over each of the D actions that this algorithm has available to it, its regret to that action is guaranteed to be upper bounded by R of t for all transcripts t. Okay, so something like multiplicative weights has a worst case regret bound of R of t on the order of like square root log d times root t. Okay, so like we've been dealing in worst case regret bounds this whole time. This thing kind of looks like root t. Maybe it picks up a log dependence on the dimension. Then, in any d-objective optimization game, the AMF regret of this algorithm is also bounded by exactly the same thing, by R of t. Meaning, if I look at the maximum over all d of the coordinates of the sum over all t of the rounds of the loss in that coordinate at round t compared to the AMF value of the game at round t, that this is going to be guaranteed to be less than R of t. Okay, so the reduction isn't even lossy. You plug in multiplicative weights, you get in this multi-objective optimization problem exactly the same regret. Okay, so we'll prove that next. Until then.